Guys, it's your favorite reliability test guy here with another fun-filled, action-packed video on reliability tests and validation topics. This current video is part 1 on a video series on MIL-STD-810, the environmental standard for military systems and sometimes commercial products too. I hope you enjoyed this video, and if you do, don't forget to hit that like button, subscribe to my channel, and ring that bell. Alright, let's get started. In this video, we will cover definitions, a background and history on MIL-STD-810, and we will introduce some of the testing we will cover throughout this video series. This is the first video in a 5-week series on MIL-STD-810H, so stay tuned each week for a new video on MIL-STD-810H. So what is MIL-STD-810H? MIL-STD-810H is a standard for planning and execution of environmental testing primarily for military systems, but can also be used for qualification and reliability testing on commercial products as well. There are many different military standards, but we will cover the standard for environmental testing in this video series for military systems and hardware. The -810 is the document number for the environmental standard, and H is the revision. It is important to note that, like many standards, MIL-STD-810H is a guideline for tailoring your environmental tests. It is important to note, like many other standards, MIL-STD-810H is a guideline for tailoring your testing program for your system, and it is not a test procedure. You will need to make sure that the recommended stress levels in MIL-STD-810H match your system's actual field use cases and stresses that it will encounter during its mission time or operational life. Let's go ahead and jump into a brief history of MIL-STD-810. MIL-STD-810 was released in June 14, 1962. The first edition of MIL-STD-810 had one sentence on allowing modifications to tests based on environmental stresses, but evolved over time to the comprehensive document that you see today. There weren't any significant updates to the first release in 1962 until the release of MIL-STD-810D in 1983, when meat really got added to the standard, including significant details on vibration and shock environments and guidelines. And the rest is history, with the comprehensive document that is used today, and more content is added through the following 3 editions, which has brought us all the way to MIL-STD-810H. The MIL-STD-810 is managed and updated by a group of military and civilian contributors and members that evaluate the standard based on current technologies and systems and field applications today. And they update the document from time to time with either a change notice or an entire new revision if the number of changes is significant. MIL-STD-810H is broken up into 3 sections. Part 1 includes roles and responsibilities, planning and program management, and tailoring of your environmental test plan based on MIL-STD-810 guidelines. Part 2 covers a large set of recommended environmental tests that can be used as part of a laboratory testing and simulation sequence or as part of field testing to ensure that your system will be able to survive the mission profile and stresses endured during its operational life. The tests and stress levels are a great baseline for tailoring the test plan for your system, but you should do your own due diligence based off of simulations and field testing to ensure that you have captured all of the potential stresses that can produce failure modes and that stress levels are adequate for your particular system. In fact, some of the stress levels in the MIL-STD-810 can be too severe for certain systems, as with the General Minimum Integrity Vibration Test under Figure 514.8E-1. Category 24, which is why the language for the Minimum Integrity Vibration Test was changed between MIL-STD-810F and G to state that the levels may be too severe for field applications and that an attempt should be made to tailor a field representative test for vibration. Therefore, take care not to just go and copy and paste tests from the test levels in MIL-STD-810H for your system without knowing whether or not the stress levels and tests represent the field use cases for your particular system. Part 3 is great because it has a lot of information and resources for selecting environmental conditions that fit a system's particular field use cases during the operational mission life. We will cover parts 2 and 3 in greater detail in following videos in this series, so stay tuned for next week and the weeks to come for more videos on this topic. For this video, we will be doing a brief introduction for part 1 of the MIL-STD-810H, so let's get started. Part 1 includes scope, applicable documents, definitions, and general program guideline. We will focus briefly on the scope section and the general program guidelines section of part 1. Under the scope section, let's briefly cover Figure 1.1, Environmental Engineering Program Guide. Pictured is the process and decision matrix for planning and preparing for an environmental testing program. This process shows the planning, preparation steps for preparing environmental testing on military systems. One interesting note is that the decision tree here has a question posed whether test hardware or prototypes will be used for testing. If the answer is yes, then you will procure parts and build test hardware or test prototypes. But if the answer is no, then you will need to run virtual testing or simulations, component or subsystem testing, or the system needs to be comparable to other systems that have historical environmental data and are field proven. In terms of military contracts, it would be tough to just arbitrarily skip physical testing, but in the commercial spaces, there really isn't any direct customer oversight. However, don't try to arbitrarily cut out physical testing to save on costs or schedule, as you will pay the price in the form of warranty costs, loss of customers, and loss of brand equity. Let's go ahead and skip to section 4 on the program guidelines now. A lot of these sections consist of roles, responsibilities, and blah blah blah, and a bunch of program management stuff that you engineers don't care about, and program and documents that need to be generated. For time's sake, we will go ahead and skip all of this and jump straight to Figure 1.48. Pictured is the generalized life cycle for military hardware. This figure covers handling, shipping, transport, storage environments for military systems. If you don't know where to start, this is a good baseline. The first column handles handling and transportation environments for road shipments. These tests include mechanical and environmental tests that the system will encounter under placing the system into a truck or vehicle and driving the vehicle for a period of time to its next destination. For transportation and handling tests, I recommend performing these tests in the packaging that the system will actually be physically shipped in and transported, as this provides a realistic use case for the environment conditions. Using in packaging will apply to all of the columns that we cover in this discussion. The next column covers rail transport. Similar tests, but the load cases would differ from what you would see from shock and vibe on a locomotive compared to road vehicles. The next column covers air shipment, which could be a propeller or jet aircraft or even a helicopter. Not only would the mechanical load cases differ between air shipments and the two forms of ground shipments that we just discussed, but the load cases would also differ depending on the type of aircraft that would be used for the shipment. One big item that you will need to think about is how will the military get it onto the ground? Will the aircraft and the system be simply unloaded, or will it be dropped from the aircraft into a war zone with a parachute? The shock levels will change drastically based on whether the shipment is unloaded or it is dropped out of an aircraft. Next, we will cover shipping and handling by sea. This can have all kinds of unique load cases, including the system sliding back and forth and slamming against the walls inside of the holding bay as the ship sways through rough seas. We now jump into shipping and logistics. This is basically the point where the system is almost at, or the system is at, its final destination. The first column in this section covers rough handling and shipping. This is where you are in a remote environment that can be very harsh and have very harsh vibration, shock, and temperature conditions. This is where some guy throws the system into the back of a truck bed and drives over washed out dirt roads, rocks, or in blazing hot temperatures in a desert or a frozen wasteland on some mountain somewhere in the dead of winter. The last two columns cover storage in either an enclosed shelter. Yes, you are actually looking at an igloo as an example of an enclosed storage location. That's too funny. The final column covers unsheltered storage, where your poor little system is just thrown out in a tarmac in a desert, getting blasted by the full fury of the sun, or buried in snow in the dead of winter. Storage conditions should not be overestimated and can really wreak havoc on your system when sitting for long periods of time in extreme weather and temperatures. Let's go ahead and cover Figure 1.4b now. Pictured are the mission or operational conditions that the system will be subjected to based on its application and use. The first column covers ground troops and all of the environmental stresses that a system could be subjected to when used by soldiers on the ground. You might think of this as just guns, but there are a lot of equipment that soldiers lug around in a battlefield. This includes things such as radios, satellite phones, and other systems such as laser systems for ranging and marking enemy targets for missile strikes. Portable troop-carried systems can be dropped on rocks, in mud, and in water, and so they can be subjected to a lot of use and abuse on the ground and in soldiers' hands. You will need to consider potential environment stresses that the portable systems will endure when developing your environmental test and evaluation master plan for ground troop systems. Next up, we have wheeled and tracked vehicles. These are anything from a ground-to-air missile launch vehicle to a tank to a Humvee and so forth. The mechanical loads will vary between wheeled and tracked vehicles, and we will cover this in upcoming videos as part of this video series on MIL-STD 810H, so sit tight and stay tuned. The next list of tests is for seafaring vehicles, such as warships or aircraft carriers and so forth. Vibration and shock still have their homes even on these sea vessels, so you should look out to test for these mechanical load cases, but one of the most severe environmental stresses that a system will endure on the sea is corrosion. The ocean is a nasty place for metallic and electrical components, so you will need to design for corrosion in mind. Next, we have airborne systems. These are all the goodies that get instrumented onto a military vehicle, such as designators, targeting systems, gun turrets, and missiles. The vibration loads are typically higher frequency as a result of the jet engines, and the temperature climates can be quite severe. For instance, flying at a 50,000 foot altitude and a temperature of roughly -57 degrees Celsius, and then descended into a desert at 55 degrees Celsius. The thermal shock stresses from these environments can be quite intense, and too much for a system that is not designed without considering thermal shock environments. Also, altitude can be a real killer for poorly designed systems as well, as you need to consider things such as rapid decompression, which can wreak havoc on pressurized systems. Also, you will need to consider the corona effect, which is where air surrounding a high voltage conductor becomes ionized and causes the voltage to travel through the air to neighboring conductors. This can be really bad, causing shorts and undesired functions of aircraft systems. So keep that in mind when spacing your high voltage conductors and neighboring components to the electrical instrumentation and circuits. Now we jump into artillery. These are those cannons that obliterate whatever they hit. Just like firing a tank, the shock from firing one of these cannons can be extremely high in amplitude, so keep that in mind when designing any sensitive systems or instrumentation that is attached to this weapon system. Next up is torpedoes, the underwater missiles that you don't want to encounter. The sight of the submarine makes me think of one of my all-time favorite movies, The Hunt for Red October. Re-verify our range to target. 1 ping only. Again, this can be a rough place to consider all of the potential environmental stresses in a battlefield under the sea, which can be induced on your system. And last but not least are rockets and missiles. Think ICBMs or intercontinental ballistic missiles, counter-defense missiles to stop us from getting nuked, and so forth. Again, some pretty intense vibration loads will be induced on your system, along with the thermal shock environments, corrosion, and so forth. So think, what can my system endure while attached to a bundle of doom and annihilation, and refer to the tests under this column to get you started as a guideline. Before we hop over to a quick review of the tests that we will go into more detail in upcoming videos, let's discuss section 4.3.3. This section covers methods you should consider for execution of your environmental testing efforts for your system. The first to consider is the natural environment or field testing. This is where you mount your system or use your system in the end operational configuration that it will be used in out in the field, or should I say out in the battlefield. This is great because you get to test your system out in the wild under real environmental stresses that it would encounter. Field testing is also an excellent way for developing the environmental test profiles that you will use as part of your environmental simulations that will be performed in a test lab. Field testing is also excellent for developing the environmental test profiles that you will use as part of your environmental simulations that will be performed in a test lab. Whenever you have the possibility of collecting field data to use for a baseline or for simulating your environmental stresses, do so, as it will pay off in the long run with a more representative environmental test plan that is tailored specifically to your system and the load cases and the mission profile that it will encounter out in the field. The second item is laboratory simulations. This is where you put your system on a vibration table or in a temperature chamber and so forth and simulate the stress environments that your system will see in the field. In military testing terms, this is done first in IRAD, which is R&D, testing for prototype systems, and then qualification testing for your product intent system, acceptance testing, ongoing reliability testing, also known as ESS or environmental stress screening. Whenever possible, your testing activities should go as follows. Field testing and data measurements to create environmental test profiles, laboratory tests or simulations in a test lab, and field confirmation testing. Typically, field confirmation testing is performed by your customer, which will be a branch of the military. Their test guys go crazy with your system and beat it and push it to the limits. So make sure you have accounted for all misuse and abuse cases as part of your environmental test plan. Alright, let's go ahead and jump into a quick discussion on part 2. In upcoming videos, we will cover the following tests in more detail, including why each test is performed, some test examples and profiles, failure modes to look out for, and what systems each test would be applicable to, and test equipment that would be used for each type of test. You can also get up to speed on many of these following tests by checking out my playlist above on environmental testing. The first test is low pressure testing, aka altitude testing. This test can be used for both shipment and operational use cases for air transport and airborne mounted systems. Next up is high and low temperature. Hot and low temperatures are actually both separate sections in MIL-STD 810, but I wanted to combine them for time's sake for this list. High and low temperature testing represents harsh high and low temperature conditions that your system will encounter in the field. This applies to every type of system from airborne to ground systems and transportation. We then have temperature shock testing. Temperature shock is a temperature cycling test, but with very high ramp rates. This can simulate things such as aircrafts landing in a desert after a long sustained flight at high altitudes. Next up is contamination by fluids. Accidents happen, that is why this test exists. It evaluates chemical resistance and compatibility of materials when exposed to chemicals it could potentially encounter in the operational environment. Next is solar radiation. This simulates direct constant exposure to sunlight. This is a critical test for all outdoor systems. We then have rain. Again, this is applicable to outdoor systems, but should also be evaluated as part of a shipping and handling test plan. Then we have humidity. This is an exposure to tropical jungle, swampland, and other high humidity environments. Next, we have fungus. Fungus can wreak havoc on electronics and materials, and fungus testing simulates high humidity environments that are a thriving, fertile ground for fungus growth. Next, we have salt fog. This represents environments such as marine environments, but can also be used for corrosion evaluation due to road salts in a cold weather environment where the road gets icy and road salts are used. With sand and dust, we are testing for ingress protection of a system, as dust is getting into an enclosure of a system can potentially cause reliability, functionality, and even safety issues in some cases. Next up are explosive atmosphere tests. These tests test to ensure that a system does not ignite when in a combustible environment with a combustible atmosphere when it is turned on or activated. Think flipping a switch in a room full of natural gas. It's going to be a bad day for you if that happened. Immersion testing is assessing whether or not your system's enclosure can keep out water when the system is immersed or dropped into water. Next up is acceleration testing. It is a test we run with a centrifuge. This test simulates loading of structures, mounts, and electrical and electronic components to a steady state inertia. Next up, we have vibration testing. This is where your mechanical loads for road vehicles, jet engines, rocket engines, and so forth are tested. Next, we have acoustic noise. This is where you evaluate your system for high-level acoustic events. Then we have shock testing. These are your potholes, crashes, and other environments that send a transient oscillation through your system. We then have pyroshock. This simulates shock events typically from expected and intentional detonations. Think stage separation of a rocket. We then have acidic atmospheres. This is another type of corrosion test using an acidic chemical or chemicals and can simulate things such as acid rain. We then have gunfire shock. As the name implies, these are shock load cases that occur when a weapon is fired. Next up, we have combined environment. This can be vibration over temperature, temperature, humidity, and altitude, or a combination of all for a really good time. What a comprehensive list, and a lengthy list too. But we are almost done here. Next, we have icing and freezing rain. This simulates conditions where it may have rained heavily during the day, and then liquid water freezes overnight. Next, we have ballistic shock. This differs from pyroshock as it is not an intentional or desired shock event, but a shock event that occurs when the bad guy hits your vehicle with a missile or rocket and some other type of ordnance. You sunk my battleship! Then we have vibroacoustic and temperature. This testing is testing for the effects of combined environment of vibration, acoustic, and temperature stress environments. Next up, we have freeze and thaw. This is where you are simulating the stress environments where a system freezes overnight and then thaws in the morning, or freezes and then thaws when the system is turned on and warmed up in a freezing environment. Alright, we're down to the last 3 tests now. First, we have waveform replication. This is where you take field data and replicate it to the signal on your electrodynamic shaker. This could be anything from road load data to an accelerometer on a portable device carried by a soldier, or data acquisition from an aircraft flight. Then we have rail impact. This is pretty cool because it is a crash test with a train. So yeah, you know this is going to be a fun test to run. And finally, the last test is quite a mouthful: mechanical vibrations for shipboard equipment, which is broken up into environmental and internal excitation sources. And that's it, folks. Some key takeaways from this video are: MIL-STD 810 was developed for environmental testing for military systems and hardware, but it can be applied to commercial products, especially if you are trying to build a brand for ruggedized products. As a consumer, however, be careful when purchasing a product that claims MIL-STD 810 drop or shock or vibration or whatever else they claim and put into their marketing mumbo jumbo. There are ways to make a claim to be compliant to MIL-STD 810 without actually running the test, and this isn't really regulated, so keep that in mind. Use MIL-STD 810H as a guideline and a reference, and not a test procedure. This document should be treated as a guideline and a reference, and don't arbitrarily copy and paste tests and stress levels from MIL-STD 810 without actually understanding what your system's environmental stresses or load cases actually are. Determine the tests that represent your shipping and handling and operational stresses. Use historical data at your company or talk to your customer. The MIL-STD 810 is a good start to what you need to do, but you need to tailor the environmental test plan to your specific use cases and application. Thank you for watching this video. Stay tuned for the rest of the video series on MIL-STD 810H in coming weeks. If you have any questions or comments or need help with MIL-STD 810 test development or test execution, feel free to reach out to me at the link above. I hope you enjoyed this video, and if you did, don't forget to hit that like button, subscribe to my channel, and ring that bell. Thanks again for watching, stay safe, and have a great day!